This is Unit 10, and we are in Notes 2. Today we are going to be looking at polar equations and calculus. So specifically, we're going to be looking at the slope of a polar curve and the area inside of a polar curve. All right? So today, let's start off by looking at the slope. So slope is always dy dx. Slope is always dy dx. When we were in parametric equations with position and velocity and so forth, in parametric equations, we said that dy dx was dy dt divided by dx dt. Leibniz's notations make it look like it's supposed to look. It's algebraically correct, because if you came in here and multiplied by dt over dt, you would get dy dx, and everything is perfect. It's so clear. That's one of the things about Leibniz's notation that is nice. One of the many things. So in polar form, if we want dy dx, remember that we're going to have r as a function of theta. In polar equations, r is a function of theta, right? So dy dx, since theta is our independent variable, we're going to need dy dx to be dy d theta over dx d theta. All right? Now, we're going to have an equation with r as a function of theta, not y and x as a function of theta, right? So how are we going to get y and x involved? Well, we're going to use those two facts. Y is always r sine theta. X is always r cosine theta. And we'll be given r as a function of theta. Therefore, we can write y as a function of theta and x as a function of theta. So in this first example, we're asked to find the slope of the tangent line to a curve. Slope of a tangent line to a curve is always dy dx. So think that. I have to get dy dx. Don't try to memorize things. Just know. Slope of a tangent line, that's dy dx. Great. Well, our curve is r is equal to 2 plus 2 sine theta, right? So we know that y has to be r sine theta, where here's r. So y is 2 plus 2 sine theta times sine theta. We can take that derivative. It's not too hard, right? X will be r cosine theta. Another thing that's not too hard to take the derivative of, right? So we're going to come off to the side. Dy dx will be y prime of theta, or you can write that as dy d theta, right? Divided by x prime of theta. It's not hard. So there's our y, there's our x. So for this to take this derivative, we're going to use the product rule, because we have a product of two functions, r and sine theta, right? So I'm going to start with r and take the derivative. The derivative of r, the derivative of 2 is 0. The derivative of 2 sine theta is 2 cosine theta. And then we multiply by the sine theta left alone. Plus, now we're going to leave r left alone, so 2 plus 2 sine theta. And we're going to multiply by the derivative of sine theta, which is cosine theta. So we found y prime of theta. Now we can go find x prime of theta. All right? So down here, another product rule, of course, because again, we have r times cosine theta, product of two functions. Start with r, take the derivative. It's always going to be the same as the derivative that you just found for y, so that's still going to stay 2 cosine theta. This time we're multiplying it by cosine theta, all right? I'm not going to put a plus quite yet because I know it's coming, so I'm going to leave that blank for just a second, all right? Now we're going to leave r alone So when you're finding dy dx of polars, these two will always be the same, right? Because this is r prime and that's r prime, and this is r and that's r. Okay? And now we're going to multiply by the derivative of cosine theta, which is negative sine theta, right? So that's why I didn't put a plus here. I'm going to pull that negative out front there and make that negative sine theta right there. Okay? So there's definitely a pattern that you can use here. But I don't like to memorize things. I would way rather know what I'm doing, right? So this is just the product rule. Okay, now we are going to, that is the derivative. That would be a safe stop, right? Now we just have to plug in pi over 6 for theta. Okay? So we're plugging in pi over 6 for theta. Now, if it was an FRQ, a safe stop would be rewriting this whole thing and putting pi over 6 in for every theta and then stopping. That would be a safe stop spot. These will more likely be multiple choice questions though. So I'm going to go ahead and put it in and evaluate the trig function at pi over 6 and simplify, because that's how you'll see it more likely. All right? But hey, if there might be an off chance that you might see this on an FRQ. So if so, definitely safe stop. All right. So 2 times, okay, cosine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. So this is going to be 2 times square root of 3 over 2 times sine of pi over 6 is a half plus 2 plus, okay, 2 times 1/2 is 1. Cosine of pi over 6 we said was square root of 3 over 2. All over 2 times square root of 3 over 2. That's always going to be the same there. Times cosine of pi over 6 is another square root of 3 over 2 minus 2 plus 1. That will stay the same. These will always stay the same, right? So take your time finding this one because you'll be using that same thing down here. Times sine of pi over 6 is a half, right? This will be another safe stop spot, but we're going to keep going. All right. This 2 cancels out with one of these 2's, and we're left with square root of 3 over 2 right there, right? This is 3 square root of 3 over 2, so can't do anything with that. Over, all right, one of these 2's cancels here. Square root of 3 times square root of 3 is 3. And then this is 3 halves, right? Like that. What happened? The denominator is 0. So our slope at theta equals pi over 6 is undefined. What does that mean? What does that mean this tangent line looks like if the slope is undefined? We have a vertical tangent line. That's what it means. Okay, we don't have to say that because they just asked us to find the slope. We found the slope. But what it means is we have a vertical tangent line. Okay? All right. We could take a look at that graph there. Let's do it since we have time. This is from yesterday. All right. Okay, let me just go look at the curve here. 2 plus 2 sine theta. And I'm just going to make sure I go 0 to 2 pi. That'll get me the whole thing. This is a little cardioid. And then I'm just going to zoom for. So at pi over 6, where's theta equals pi over 6? Theta equals pi over 6 is like right here, right? Can you see that vertical tangent line, how that would be a possibility at theta equals pi over 6? I can. I hope you can. All right. Makes sense. All makes sense. All right. Example 2, find the slope of the tangent line to this polar curve. This is a rose, right? A rose, each petal is length 1, and there are 3 petals. The first petal is on the positive x-axis. Okay? We want to find the slope of the tangent line to the curve when theta equals pi over 4. There should not be a period right there. Anyway, that's all right. All right? So, think to yourself, I need the slope of the tangent line. That has to be dy dx. Has to be dy dx. How can I find dy dx? Well, y is equal to r sine theta every time. Every time. X is equal to r cosine theta every time. R sine theta for y, r cosine theta for x. So dy dx will be dy d theta divided by dx d theta, or you can totally write it y prime of theta over x prime of theta. That's fine. Okay? So a product rule, right? Because we have a product of 2 functions. The derivative of cosine of 3 theta is negative 3 sine of 3 theta. Okay? Times sine theta plus, now we're going to leave cosine of 3 theta alone and multiply by the derivative of sine theta, which is cosine theta. All divided by dx d theta. So r prime negative 3 sine 3 theta times, we're going to leave this cosine theta alone. We will end up having a minus here, so I'm going to leave that blank for a second. Leave your cosine 3 theta alone and multiply by the derivative of cosine, which is negative sine theta. Okay? There's dy dx in terms of theta. Now we just have to plug in theta equals pi over 4. So again, a safe stop answer would be just replacing every theta with pi over 4 and stopping. That would be a safe stop spot. But for multiple choice, let's go ahead and work this out. So I'm going to have this negative 3 times sine of 3 pi over 4. That's over in quadrant 2. Sine is positive. So this is just square root of 2 over 2. Times sine of pi over 4, square root of 2 over 2, plus cosine of 3 pi over 4. Second quadrant, cosine is negative, so negative square root of 2 over 2, times cosine of pi over 4, positive square root of 2 over 2. All divided by, okay, this is going to be the same thing that we had up here, right? So negative 3 square root of 2 over 2. Cosine of pi over 4 is square root of 2 over 2 minus that's going to be the same thing that we had up here, negative square root of 2 over 2 times sine of pi over 4 square root of 2 over 2. All right? So let's clean this up. Do you guys see all of the denominators that have a 4? What's a quick way to get rid of that? Let's multiply top and bottom by 4. We're not changing the value, right? Because we're just multiplying by 1. So this is going to be negative 3 times square root of 2 over 2 times square root of 2 over 2. So negative 3 times 2, that's going to be a negative 6. I almost put a plus there. It's going to be a minus. Minus square root of 2 times square root of 2 is 2. Divided by, okay, these 2's are now gone, right? So negative 6 plus 2. Square root of 2 over 2 times square root of 2 over 2. So this is negative 8 over negative 4, which is 2. Okay? So on those, practice those, because the more you practice, you're going to get really good at plugging in these values again. You were really good at it, I'm sure, last year when you were doing it full time, and you've slept since then. So go ahead and get a little practice putting those in. Okay. Okay, let's go on to something else. All right, let's consider, let me try to sharpen that up. It sure does look blurry. Okay, consider the polar curve, okay, r is equal to 3 plus 6 cosine theta, whose graph is shown from 0 to 2 pi. This is how I see these worded out sometimes on the AP exam, all right? For what values of theta, in theta between 0 and 2 pi, is r positive? All right? R positive. So r is greater than 0, right? Well, that's not hard. We know what r is. Set it equal to 0 and do a sign chart, right? Sign chart. Whenever you're trying to see where something is positive or negative, sign chart. Okay, so I know what r is. 3 plus 6 cosine theta. Set that equal to 0, solve for theta. If we subtract 3, then divide by 6, we're going to have cosine theta is negative 1/2. So the values of theta that make r 0 would be the values of theta that make cosine of theta negative 1/2. So we're talking about the second and the third quadrants, and we're talking about pi over 3 angles. So 2 pi over 3 and 4 pi over 3. Those are the values that go on our number line. And we know we're bounded by 0 and 2 pi, right? So 2 pi over 3, 4 pi over 3, and we're just doing a sign chart for r, not r prime. This is just r. We just want r to be positive. So this is just r here. Okay, so we do know enough about cosine to know that it is cyclical, and where r is 0, we're going to change signs, right? So use your head on this, right? This is just a cosine graph. So cosine doesn't like bounce on the x-axis, right? So use your head on this. So I think I'll pi over 2 is a nice one to put in. I think I'll put pi over 2 in. Pi over 2 would be in between 0 and 2 pi over 3, right? If I put pi over 2 in for theta, cosine of pi over 2 is 0. So we have 3 plus 0. That's positive. So this is positive right here. And so I know this is going to have to be negative, and this is going to have to be positive. Again, because we know we've spent a whole semester doing trigs, so you should know that cosine goes from positive to negative when it's 0. All right, or negative to positive. Okay, so r is positive on 0 to 2 pi over 3 and 4 pi over 3 to 2 pi. Okay? Not bad. So guys, you might be asked things that you just need to use your head and use your plain old math knowledge, your logic, and answer the question. Okay? Part B, for what values of theta in between 0 and 2 pi is r increasing? R increasing. So this time we want r to be increasing. Well, in class I usually say, okay, everybody, close your eyes. How can you tell if any function is increasing? What was our test? What did we use way back in function analysis? How can we tell when any function is increasing? And somebody will usually say, oh, the derivative is positive. And I'll say, open your eyes, that's exactly right. We want the derivative of whatever function it is to be positive. So we want r prime to be positive. Okay? That's how we tell when a function is increasing. So we're going to do the same thing. We need a sign chart. This time the sign chart needs to be for r prime. So we're going to come down, find r prime. What is r prime? Well, the derivative of 3 is 0. The derivative of 6 cosine theta is negative 6 sine theta. So we're going to set that equal to 0 and solve for theta. This will be all the values of theta that make sine 0, right? Sine of theta 0. Well, theta will be, sine of 0 is 0, so 0. What's the next value of theta that makes sine 0? Pi, and then 2 pi. I don't want to go further because that would be out of my restricted domain here. So my sine chart will be from 0 to 2 pi. Those happen to be my boundaries. And I'm doing a sine chart on r prime because that's what I'm trying to figure out. Okay? Pi over 2 is another nice one to put in. So what is sine of pi over 2? Well, sine of pi over 2 is 1, but negative 6 times 1 will be negative. And again, use your head. Sine does change signs when it goes through the x-axis, right? So this will be positive there. So r will be increasing, okay, in this interval. Now recall, for increasing, that was the one concept that we did include the boundaries. Do you recall that? It was the one that we included the boundaries on, and it's just because of the definition of increasing and decreasing. Okay, so I'm going to write r is increasing when pi is less than or equal to theta is less than or equal to 2 pi. And that's it. Okay? If you had to justify your answer, you would say since r prime is greater than 0 on this interval. Okay? That is true. All right, let's take a moment here and let's look at this graph. All right, so on this graph, when r was positive, where are we? Where are we on the graph when theta is 0? If you put in 0 for theta, cosine of 0 is 1, 3 plus 6 is 9. So when theta is 0, we're way out here at 9. That's when theta is 0. As theta moves, as we go to pi over 6 and pi over 4 and pi over 3, etc., the curve, look what's happening. Look what's happening. R is still positive. R is still going to be positive. It's out here at 9 now. R is still positive. But what is R doing? R is not, it's not staying out at 9. If it was staying out at 9, we'd be making a big circle, right? That would be R prime would be 0. Well, R wouldn't be a constant then. So here, R is decreasing, isn't it? R is decreasing, 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 decreasing. R is still positive, but it's getting smaller, right? I know it is because when we get to here, it's 3. Right? So we went from 9 for r to 3 for r, and then it keeps getting smaller. And then what happens right here for r? R is 0, isn't it? So at that value, we're at 2 pi over 3 for theta. Okay, and as we keep on going, now r is negative. R is negative, which means r is still decreasing in value. R is still decreasing in value because it's getting more and more negative until we get to this point, which must be pi. Because after that, r begins to increase. it gets less negative and less. It's still negative. R is still negative, but it's going towards the positive. And now right here at 4 pi over 3, we reach R is equal to 0. And then R becomes positive, and R continues to increase, 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 increase. Here it's 3, increase, 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 until we get to 9 again. Okay? So what we did with these charts totally makes sense. Totally makes sense. Okay, part C. For what values of theta, still in this interval, is the distance between the origin and the curve increasing? What is the distance between the origin and the curve in this problem? Well, the distance is always the absolute value of R. Okay? So that's our function that we want to know when it's increasing. The distance is the absolute value of R. To tell when any function is increasing, you take the derivative and see where it's positive, right? How do we take the derivative of an absolute value? Do you recall way back when we did rectilinear motion, and we were trying to see when the speed, and I said then, let me get a piece of scratch paper here. I said to you then that speed was the absolute value of velocity, and we wanted to know when is speed increasing and when was it decreasing. And I said back then, we need to take the absolute value of, we need to take the derivative of that absolute value of v. And I said, that's not an easy thing to do. Do you remember me saying that? It gets complicated if you don't have a calculator. If you have a calculator, not complicated at all. But let's assume we don't have a calculator. That's complicated, okay? So I said use the result. Do you recall that? I said use the result. I said speed is increasing when v and a have the same signs. And speed is decreasing when v and a have different signs. So we're going to use a similar thought process here. All right. The absolute value of r, its derivative is positive when, so the distance is increasing when, okay, when r and r prime, because we did v and v prime, so r and r prime have the same signs. Okay? All right, so that's what we're going to be looking at. So we want to know when r and r prime have the same signs. We've already got the sign charts for both of those. We just need to combine those into one sign chart. So I'm going to do one sign chart. We're still going from 0 to 2 pi. Our first stop will be 2 pi over 3. Our second stop will be pi, and then 4 pi over 3, and then 2 pi. And since we did r up here, I'm going to put r on top, and I'm going to put r prime on the bottom. Of course, that doesn't matter. Just keep it straight. All right? So r was positive between 0 and 2 pi, negative between 2 pi over 3, I said 2 pi over 3, negative from 2 pi over 3 and 4 pi over 3, so negative, negative, and then positive the rest of the way to 2 pi. R prime is negative between 0 and pi, and positive between pi and 2 pi. So where do these have the same signs, and where do they have different signs? Same signs right here and right here. Okay. So the distance is increasing on, and this is another increasing question, so I'm going to include these boundaries, right? So on 2 pi over 3 less than or equal to theta less than or equal to pi, and 4 pi over 3 less than or equal to theta less than or equal to 2 pi. All right? And that makes sense too. If we come back up here, right here, since r is positive, r is positive positive here and r is decreasing, and the distance between the curve and the origin is decreasing there. So that makes sense until we get to 2 pi over 3 right here. Then r is negative, and we're decreasing. So r is negative and we're moving out. We're getting more negative. It's negative and getting more negative. So of course the distance will be increasing here. And then from here, from this spot to this spot, the distance is now decreasing again until we get to 4 pi over 3, and then the distance increases the rest of the way. Totally makes sense. Okay, I'm going to pause for a second. Okay, it's time for us to take a look at area. So I'd like to show you where we get the area formula for, okay? Back when we did area underneath a curve in Cartesian coordinates, so this was at just f of x, okay, y is equal to f of x. When we did that, how did we develop the area under the curve? Do you recall? We did that with rectangles. Why? Because rectangles have an easy to find area, yeah? So we approximated this using rectangles, right? And we found that each rectangle had an area of height times the base. Height was f of x in general, and the base was delta x each time. So that was the area of one rectangle. To get the area of everything, we added them all up. We had I to help us keep count of our rectangles, and let's say we have n rectangles, so we're going from 1 to n. And then we want to let n go to infinity to get the area under the curve rather than just all these chopped up rectangles. And when we did that, we got the integral from a to b of f of x dx. Okay? So that was the area under a curve. Okay? Now we're in polars. Let's take a look at this one. So now let's say that this is r is equal to f of theta. Okay? How are we going to approximate the area inside, or a partial area? How are we going to approximate area now? Rectangles are not ideal in this situation, are they? They're not ideal at all in this situation. What would be more ideal? Well, what would be more ideal would be little sectors. Little sectors. A sector is part of a circle. Part of a circle. Part of a circle. Okay? So if we took sectors, and I'm drawing them wrong because I drew this circle just, or this limicon just a little bit too curvy. Usually they're not curvy enough, but I think you get the idea. Each of these is part of a circle. Okay? So each of these is a sector. And this would totally work. right? To approximate the area. My little red pen is going out already. It's kind of new. Okay. All right, so some of these little sectors, well, the way I'm drawing it, some are above the curve and some are below the curve. I wanted you to get the idea that they're not exactly the curve, because this curve is not a circle, right? But I'm not doing a very good job of, because they would all here, all of these should be beyond on the outside of the curve. I just didn't draw it right. Okay, anyway, you get the idea that if we added up each of these areas, we could approximate the area of this figure, right? If we kept on going around. We keep on going around. And then we keep on going around. We can approximate the area of this figure. My question is, what is the area of one sector? Okay, I'm going to have to switch to another color. What is the area of one sector? Okay, back in geometry, you did this, all right? The area of one sector is 1/2 r squared theta. That's what it is, 1/2 r squared theta, if and only if theta is in radians. This formula does not work if theta is in degrees, all right? And I could show you where this comes from. It's not too hard, but let's just go on. That is the area of one sector, okay? All right, so what are we going to do? Well, we are going to take all of the areas and we're going to have little tiny slivers of theta here. Instead of little tiny slivers of x, we're going to have little tiny slivers of theta. So this is going to be delta theta in here. That's going to be one area of the sector, or the area of one sector. What are we going to do? We're going to add them all up. And we're going to keep count of them from 1 to n, where n is the number of sectors this time. Instead of the number of rectangles, it's the number of sectors. And then we're going to, how do we get the exact area and not these chopped up things? We let n go to infinity. And we get the integral, okay, from, I'm going to say a to b, but remember those are now theta values. Those are theta values of 1/2 r squared d theta. That's where the magic is. Okay? So, how do we get the area of this entire figure if it is a limacon? Well, a limacon would need to go from 0 to 2 pi. Do you remember when I said we're going to need to know what values of theta form a complete graph? This is when you need it. Okay? What if you were asked to find just the area from 0 to pi? Then you would just use 0 to pi. What if you were asked to find the area in the first quadrant? Then you would use 0 to pi over 2. We don't have to start at 0. We could start at pi and go to 3 pi if we wanted to, right? There's nothing magical about starting at 0. It's just convenient to do that, okay? But this is our big area formula. Now, so I will tell you that this is the formula for the area of a polar curve. This is area of a polar curve. Okay? Kids always ask me, Miss Murray, why are we taking half of the area? And I'm like, no, we're not taking half of the area. For the same reason we needed a pi for the area, for the volume, it was because pi was in the area of a circle. This 1/2 is in the formula for the area of one sector. So this 1/2 is important, okay? It's not, we're not taking half the area. That is the formula for the area, okay? All right, now let's go take a look at an example. So example 4. The graph of the polar curve, r is equal to 2 plus 2 cosine theta, is shown on the right. Find the interior area. Okay, find the interior area. It's a cardioid. So we can just go straight to the integral. The area formula is 1/2 r squared d theta. So 1/2 r squared d theta. All we need to know are the boundaries. What are the boundaries for a cardioid? What values of theta form a complete graph? 0 to 2 pi. Remember, all of these form a complete graph in 0 to 2 pi unless it's an odd petaled rose. Odd petaled roses, 0 to pi, form a complete graph. Okay, now we're going to go to our calculator and work it out from here. And I need to go back to we're doing computation, so I'm going to function mode, all right? So math 9, 0 to 2 pi. You could stay in polar mode for that, but there's no reason to. So I would suggest you go back to function mode. So get practice putting those in. And what did I do wrong? Did I not put that in right? I want to take a look at that. That's not what I got on my other sheet, but I don't see what I did wrong there. This is usually where somebody will say, tell me what I did wrong. 1/2 r squared. I don't see anything I did wrong here. Oh, 1 to 2 x. That's what I did wrong. That needs to be a pi. That's better. I was thinking my number was half of this, but it's not half of that. Whatever my value of x is, it must have been pretty close to half of pi. Yeah. So anyway, this is better. Whew, okay, 18.850. We're good. Okay, example 5. The graph of the polar curve r is equal to 8 sine of 3 theta is shown on the right. Find the interior area. Before I do, I want to come back up to this one real quick. Do you see the symmetry? We could have taken the integral from 0 to pi. That would have been just this piece. We could have taken that and doubled it, right? And we would have gotten the same answer. Okay, so you can use symmetry to your advantage on these. Okay, all right, example 5. The graph of the polar curve r is equal to 8 sine of 3 theta is shown on the right. Find the interior area. Okay, the interior area. So we know that the area is going to be 1/2 r squared d theta. What values of theta form a complete graph? Well, this is an odd numbered petaled rose, so 0 to pi, right? Okay, math 9, 0 to pi of 1/2 8 sine 3 theta squared dx. I'm kind of scared I'm going to make a mistake now. Okay, 50.265. All right, next up. The graph of the polar curve, r is equal to 3 cosine of 4 theta, is shown. Find the area of one loop. Find the area of one loop. So this is one in class I'll ask, hey, how do you think we should do this? Usually people say, oh, we can just find the area of the complete thing and then divide it by 8 because there are 8 petals. I'm like, that works. Let's do it. So let's find the area of the entire thing, the entire interior area. So that will be 1/2 r squared d theta. For an even numbered petaled rose, we need to go all the way to 2 pi. And we only want one loop or one petal, so we need to take 1/8 of that, right? That'll work. Let's put it in the calculator. So I'm going to do 1/8, math 9, 0 to 2 pi, 1/2, parentheses, 3 cosine 4 theta, close the parentheses on the 4x, close the parentheses on the 3 cosine 4x, and then square. Get practice doing this, you guys. Every year when I'm giving the test, I see kids who clearly have not practiced, and it takes them way too long to type things in. It's a workin'. There we go. That one little petal is 1.767. Okay? Now, I want to show you another way to do this. Because what if the question on my test or on AP test didn't say to find the area? What if it said which integral gives the area of one loop? And what if this was not one of the choices? Okay? Well, here's another way to think of this problem. One loop is formed by consecutive values of theta that make r 0, right? One loop is formed by consecutive values of theta that make r 0. So we can take r, set it equal to 0, and find 2 consecutive theta values and use those. All right? So let's do that. Here, we want 4 theta to make cosine 0. The first thing I think of that makes cosine 0 is pi over 2. The next thing that I think of cosine of being 0 at is 3 pi over 2. I just want 2 consecutive ones, right? So theta would be pi over 8 and 3 pi over 8. So those theta values would form one complete loop. So another integral would be still 1/2 r squared d theta, but pi over 8 to 3 pi over 8. That would be another possible answer, okay? Another possible answer. I want you to take a look at this. Something that we can do with polar curves because of the symmetry involved. Okay? Let's multiply 1/8 times each of these boundaries. 1/8 times 0 is 0. 1/8 times 2 pi is pi over 4. Using this as our boundaries would also give us the correct answer. Using this as the boundaries, we would be going from theta is 0 to theta is pi over 4. I think it would actually go over here. Isn't that the area of one petal? 0 to pi over 4 would give us the area of one petal. If that is that, it may be down here. I don't know. I don't know where it is. I don't know where it is. But anyway, you get the idea. 0 to pi over 4 would also give us the correct answer. And now I ask you this. What is the distance between 3 pi over 8 and pi over 8? Pi over 4. Pi over 4. Okay? So we can use that, and it's only true in these polar equations because of the symmetry, all right? But we can use that in a multiple choice answer where you're asked to find the integral that gives the area. You can use that fact. Okay? Let's look at another example. Example 7. Almost done for today, just a couple more. Example 7. The graph of r is equal to theta plus cosine theta is shown on the right for pi to 2 pi. Find the area between the curve and the x-axis. Okay? We're going from pi to 2 pi. So our first little sector would be right here, and then right here, and then here, and then here. Our sectors have to go, they have to go in the counterclockwise direction. Okay? So, what is that area? Well, it's just the area of 1/2 r squared d theta from pi to 2 pi. That's all it is. When you put that in your calculator, I'm going to save us a couple of moments here, we get 38.959. Okay? Example 8. Find the area of the inner loop of this lemmasome, whose graph is shown for 0 to 2 pi. All right? So we want just the area of this piece. We want that area. So do you not agree that we need to find the theta values where r is 0? So we're going to set r equal to 0 and find those theta values. Those will give us our boundaries on our integral. So sine of theta will be a negative 2 over 4, so negative 1/2. So theta is the values of theta that make sine negative 1/2. Third quadrant and fourth quadrant, and they're both pi over 6s, so 7 pi over 6 and 11 pi over 6. So this area will just be the integral from 7 pi over 6 to 11 pi over 6 of 1/2 r squared d theta. This is usually where I ask my kids, why do we need that 1/2 right there? Why do we need a square r right here? It's part of the area of a sector. That's the formula for an area of a sector. Okay, when you put that into your calculator, you're going to get 2.174. Okay, one more and then we're going to stop for the day. The graph of this is shown on the right for 0 to 2 pi. I love that graph. Doesn't it make you want to go and see what else happens beyond 2 pi? Go for it. I want you to go for it. I will tell you that the first loop that is formed is, I think the first loop that is formed is right here. And then the second loop is this one. Notice how smooth it is, you guys. When you're drawing these, you're never going to bounce at the origin. Like it's never going to go boop, boop. It's not going to do that. It's always going to be very smooth. So it's going to be here, and then it's going to come around to here. You can kind of see how it's going to go. No jerky motions though, all right? Watch it graph on your calculator. If you have an old calculator like mine, where you can watch it graph and you'll learn where it goes. Okay, you'll get comfortable with that. We want to find the sum of the areas of the loops in quadrants 1 and 2. Yikes. We want to find this area plus this area. Okay? So we need to know the theta values that form that. Well, let's first begin by finding the theta values that make r 0, because that's going to have to be done. So theta sine 2 theta, set that equal to 0. Either theta is 0 or sine of 2 theta is 0. So 2 theta would be 0, pi, 2 pi, 3 pi, 4 pi, etc. Divide both sides by 2 or multiply both sides by a half. And we get these values in between 0 and 2 pi. Okay? Now, I'm pretty sure, just from looking at the way this looks and what I just talked about with no bouncies, it's not going to go from 0 to pi over 2 and then bounce and then goes directly into this quadrant. I know it's not. All right, that would make no sense because these curves never bounce. They don't. All right. So up here, it didn't go like this and then bounce and then come back out. We started going this way, and then we did this, or maybe I think we started here. I think we started right here, and then we did this. And this, that. It's all very smooth. These curves are very smooth, no bouncy bounces, okay? So, I want to make sure that I think, here's what I think, especially now that I know this. I think we need to go from 0 to pi over 2, and that will give us that. And then I think we need to go over here from 3 pi over 2 to 2 pi to get that. But I want to confirm, so I want to look at my r values. Let's look at just our r values. I want to see where they're positive and negative. Okay. If I come here in this piece, maybe put in pi over 6. If I put in pi over 6, I'm going to have, and this is just r, pi over 6, I'm going to have positive times a positive. Okay? And now, I know enough about sine to know that this thing's going to change signs. Is it? Is it going to change signs? It is. So, negative, positive, negative. Okay? So what does that mean? I want this right here. That means that r starts off positive, so yes, I do want to go grab that piece, 0 to pi over 2. But my next piece, r, is negative, so that is coming down here. Because between pi over 2 and pi over 2 and pi is over here, right? But r is negative, so it's going to go through the origin to the other side, right? Between pi and 3 pi over 2, r is positive. So this is between pi and 3 pi over 2. And then between 3 pi over 2 and 2 pi, r is negative again, so we're bounced to the other side of the origin. For this curve, it's from 3 pi over 2 to 2 pi. So we need to add those two pieces. So we need the area from 0 to pi over 2 of 1/2 r squared d theta, and then we need to add the integral from 3 pi over 2 to 2 pi of 1/2 theta sine of 2 theta squared d theta. And when that goes into your calculator, you're going to get 12.175. Okay. Next time I'm with you, we will start looking at two different graphs put together. Fun times to come. Okay. Go practice your first day's work though.